Okay. Thanks everyone for staying up late and being so bright to come to the last session actually of the day. I think most of your colleagues are actually downstairs having a beer or something. But at any rate, I'll try to be quick as much as possible. And at the end of the presentation, we'll have actually a bit of entertainment. My colleague Brett Rudenstein will show how this stuff works in action, and that's most fascinating thing in the technology I ever seen in my career, actually, to be honest. Anyway, I am working at the company called Vandiska, which smartly stands for Wide Area Network Distributed Computing. And what we do is essentially provide an enterprise-grade level continuous availability support for clusters, right? So we do this for Subversion, Git, HDFS, and now Hbase churn has come. So what are we trying to solve, right? So essentially, I don't know, how many of you are familiar with HA technologies, high availability technologies? 1, 2, 3, 4, 5, 6, 7, 8, okay, roughly. 9, okay, good. You don't count actually. But let's say, I don't know, what, 5%, right? 10% probably of the room, a little bit more than that. But anyway, so essentially, if you think about this, what the high availability technology is, or most of it essentially, right, is an attempt to recover after a failure happened, right? So if you think about this in most layman term, we have a running system, we're trying to snapshot or copy or somehow else mirror the state of the system somewhere else so we can actually fall back to this somewhere else in the event of the disaster. So basically, trying to fix a screw up, right? So that's essentially the problem. So, and as the most backup systems, unfortunately, actually, backup systems tend to fail, right? I mean, if you have a backup, no matter how good is that, no matter how, how well it stays tested and, how beautiful technology you have underneath, RAID mirroring or what's not, there is a chance that something would not go right during the failover process or during the snapshotting process or something, right? And if you think about the traditional architecture where you have a single, that's essentially HDFS thing. It's not Hbase, but we'll get to Hbase in a second. If you think about this, here's a single master. Here's a way to copy the edit logs of whatever you're trying to copy into the shared media, NAS or SAN. Or else, or in-memory QGM cluster, QGM file system. And all the clients are working with that single master. Even if your fault recovery procedure is actually very quick, your clients need to fall over properly, right? There could be recovery timeouts, happening and what's not. And as we will see in case with Hbase, it's actually MTTR really matters, right? So, and again, the problem is that it's a single master, and as with all backups, they tend to fail, right? That's essentially the problem. Anyway, so what we do at Vandiska, we implement in active-active technology, and if you're actually interested to hear about how we solve this problem for HDFS, we have a talk tomorrow at 3 o'clock by my colleague Konstantin Shvachko, who will be talking about the replication of the metadata for HDFS. Highly technical, very interesting talk. I cannot recommend it more. But anyway, so what we do, we spread the active master to the multiple copies, right? And when I say multiple copies, it means that we have actually multiple masters actively working on the system at the same moment of time. And our technology, we'll talk about this later a little bit, guarantees that at any given moment of time, these masters have exactly the same picture of the working system, right? So basically, the idea is that the client can work with either of the masters, active masters, right, which provides native load balancing, right, in the first place. And secondly, it doesn't matter if I connected the master and it failed, I would be pretty much immediately round-robin to the next one, which has exactly the same picture of the universe as the first one, right? So the outcomes, the benefits actually of this technology are numerous, right? And we'll chat about this a little bit. But the most important one is that you actually can provide 100% availability for your distributed system. So to think about this a little bit, traditional HA can guarantee, say, 5 nines of uptime, right? So 5 nines of uptime equivalent to 5.6 minutes a year of downtime. And if your business is actually requires constant availability of your thing, right? So every minute of the downtime could cost money to you. You would be very cautious about, such a great 5 nines promises, right? So that's essentially the recapture of how the single master technology works, right? So you come in with a bunch of operations into the master. The operations are being laid out in a certain sequence and then applied on the server somehow, right? So how we can do this, how we can actually achieve the redundancy in this particular case, right? You can use load balancer, right? So load balancer will decide where the request needs to go. The negative size of load balancing is sort of obvious because not necessarily every single request would be mirrored to the other servers, right? So you might have discrepancies in the data and that kind of stuff. Hbase, for instance, has this notion of wall replication, right? A head log replication. And essentially how they do this, all the operations are being stored in memory in whatever the mem store, right? And once in a while they're being serialized to the HDFS, and HDFS sort of replicates it, and that's how you can pick up the latest set of changes if something goes wrong with the region server. Again, there are chances that the serialization didn't happen on time, and the in-memory changes got lost and that kind of stuff. So, and it's always comes to the point where you have a standby server that you need to rely on and make sure that it's actually up to date with the master one. So again, same backup problem. As I said, there's a shared storage, and you write to it, and the replication server sort of reads from it. Again, if something happens to the shared storage, you're screwed. There's other technologies like wall tailing and snapshotting and what's not. And essentially the problem here is that it takes time. If something goes wrong, your whole recovery process could be hoosed, right, and completely broken. You cannot have multiple active region servers, so actually recovery of the region server can, if you're lucky enough, right, can be like, 30 seconds. If you're unlucky, if your wall got lost or something like that, you would have to reconstruct the whole region server. You can actually end up with a couple hours of the downtime, right? And it actually goes, interestingly, to the question of MTTR, mean time to failure, to recovery, I'm sorry. There was a number of the experiments and research and what's not, where people were trying actually to find the most optimal solution to the recovery of the region server, Hbase region server. And the best result, I believe, like theoretically best, right, is 20 seconds, because this is exactly the amount of this is the shortest possible zookeeper timeout that needs to expire before you can start the recovery process. And the worst kind was, I believe, about 2.5 hours or something like that. So it's just pretty crazy. And here's the problem with that sort of recovery or fault tolerance that built into Hbase right now, is that client is sort of not aware about the whole recovery thing, right? So if let's assume you have a streaming client that actually dumps a lot of data into the Hbase all the time, right? So here's your region server goes down. The regions that we were trying to write the data into, right, they goes offline, but client is actually not aware about this fact, and you start losing the data until the recovery kicks in and you got your regions back, right? So it's pretty bad sometimes. So essentially what we do and how we're trying to solve this problem for Hbase. So DCON stands for Distributed Coordination Engine. This is our technology, multi-process implementation essentially, right? Highly optimized, which works very well, and actually been working for very well for a number of years. So essentially the idea is very simple. So whenever a client comes to one of the active masters and trying to perform a modification operation, something like put or multi or batch or whatever, before the operation happens, the request is being sent around in the form of Pax's proposal, and the quorum of the masters actually agreed that this operation can go through. Once the agreement has been achieved, the agreement is being essentially applied to the local copy of distributed state machine, the con thingy, right? And then every single master from that moment on performs the operation independently, right? Which means that before the operation even happened, we know, the correct state all across the masters. So, and there are some serialization optimizations that we do to guarantee that even if one of the masters failed during the application of the agreement has been serialized, and upon the restart, it will be able to restart it from the permanent storage, local permanent storage, and relearn the state of the system. So, again, benefits is that every single master is totally isolated from each other, right? In the sense of there is no shared state between them, right? So there is no there's no problem that something will go down like NFS or SAN in between, and you will end up with not knowing what's going on. Clients can work with either of the active masters. Load balancing is achieved through this, and which is especially interesting for the high volume systems like Hbase, right? Okay. Anyway, so I think I just covered that. Well, almost. So if you step back a little bit and see where the problems can lie in HDFS, right, where the failure can happen, what was the SPOF essentially not HDFS, Hbase. Apparently, Hbase master is a single thing, right? I mean, there is some redundant failover procedure that can kick in if the master goes down, and it requires actually, trips to the zookeeper and restoration of the state and whatnot. This is one Hbase client I just mentioned, right? So it's another point of failure. MTTR of the region server we just discussed. Another sort of like gray area is the major compaction of the regions, which not necessarily a failure, but major compaction can actually go for a long time, which means that you don't have access to these particular regions under the compaction while it's not finished, right? Which means essentially availability of the data could be limited, or you have to schedule it in advance, and all these problems. So with multiple active technologies, you essentially can take one of the masters offline, do the compaction, whatever you need to do. The others keep serving your clients. Then you can roll over the compaction role to the next one, to the next one, to the next one, that kind of stuff. So that's a little bit of sort of visual aid to help you basically grasp the idea of the multiple masters. For region servers, this is essentially like traditional Hbase representation, right? So you have HDFS, you have regions, and there's a master region servers. Region servers can hold regions, which essentially HDFS files, and clients work with region servers and doing the things with the data. So when we're talking about multiple masters, we essentially grab this black box, which is a master and bunch of region servers, and sort of spread it around. So we essentially get in the picture where we can have multiple masters, all active, multiple region servers, all active. Multiple region servers, I mean multiple replications of the same region server, and then another region server, and then another region server. And clients can work actually with either combination of master region servers and what's not. So basically, you get in a system that is highly replicated, that provides you an ability to be redundant to the extreme, essentially, right? But at the same time, it doesn't use too much hardware, which is stay idle just in case, that kind of stuff. So you essentially, increase the capacity of your system, if you will. I don't know if we should go there. Well, yeah, why not? Maybe quickly. So that's essentially the flow of the operations, right? Which we kind of touched upon. So first, the client comes from the call comes from the client, right? So for particular operation, for instance. Then the second one, the region server intercepts the call. then does the proposal, they run the proposal within the Paxos cluster. At this point, actually, the exchange between our DCON implementation happens. Then one proposal is actually agreed upon, it becomes an agreement, and it's being sent to all the replicas of the cluster, of the region servers. And at this point, every single region server calls the operation to get completed. So, yeah, and one of the clients, one of the region servers that has been regionally involved with the client will send the confirmation back. So, and essentially, that's pretty much. I think we can skip this safely for the sake of time. So essentially, one of the points I wanted to touch upon here is that unlike some of the so-called high availability solutions, the solution we're building here is essentially not an eventual consistency model, but enforced consistency model. So at any given moment of time, you can guarantee that your system is actually consistent, right? So any copies of your data, metadata, is always the same across, right? If so happened that one of the active masters lost, the connection with the rest of the cluster and become offline for a while, it will detect that he fell behind automatically and will stop serving the clients until it will, recapture the data. So that essentially almost automatically guarantees that you don't have split brain problem, right? So you don't need to fence offensive. And the best part, of course, is that you can do this over wide area network, right, which is pretty much impossible otherwise. So you can have Hbase clusters in different data centers, and they behave like the same the Hbase cluster, although there could be thousands of miles in between. I think I'll pass it to Brett to actually run the super fancy demo, and then we'll answer the questions if you haven't.
All right. Is this on? Hello? Oh, wow. Thank you, Kaz, for finding the best possible picture of me. Guys, I'm going to do a demonstration of our nonstop technology for you. Maybe just as a quick recap. If we think about it, what's underneath Hbase is HDFS. So maybe I'll do a quick demonstration of a nonstop HDFS, and I'll follow that up with the demonstration of nonstop Hbase, because you've got to have a hardened HDFS, if you will. If HDFS goes down, there's no place to write. There's no place to write the wall, there's no place to write H files, and so forth. So I'll start with a very simple cluster that I have here, but what might be a little bit different in this cluster is that you see it's spread across, it's a single HDFS cluster spread across 2 different territories. This is a map of the United States. We've got a cluster running in Northern Virginia, and then there is the second part of the cluster, it's the same cluster, running in Oregon over in the US. Now I'm going to drill down into this little mapping application. And what you'll see inside of this is that the first thing that we do is we stand up multiple name nodes in each data center. And what's important here is that I've got 3 name nodes in Northern Virginia, I've got 3 name nodes in Oregon, and it is a synchronous namespace. So Konstantin just talked about the Paxos algorithm that we use, or our distributed coordination engine. Well, one of the things that we do in terms of HDFS is we ensure that every metadata change, every metadata update that goes into HDFS or into the namespace, the Hadoop's name node, is actually replicated across every single one of those name nodes. So a client can hit any one of those, and it will immediately coordinate to all of them. Now, to kind of show you this nonstop technology, what I'm going to do is I'm going to run some of the standard sample applications. I'll run TerraGen and TerraSort. I'm going to run those 2 things in our Northern Virginia data center. And then I'll run TerraValidate inside of our Oregon data center. Remember, it's on one single cluster. And while those are running, I'm going to drop name nodes. In fact, at some point, I'll even drop the whole wide area network link. And we'll keep everything going. We'll ensure that all the blocks are replicated. That's the sort of underlying system, even for an Hbase. You've got to have the underlying system or the file system be hardened. So let's do that. I'll kick off the gen script, and I'll just put in a directory called temp1. And again, the script runs TerraGen and TerraSort back to back. And one of the first things that you'll notice is that all of the name nodes start to kind of respond to the event. They're all taking requests. The clients are round robining. They're load balancing the requests, just like in just a few moments when I get to the Hbase portion of the demonstration. The clients will be round robining their requests to each of the active region servers. Now, another thing that you're going to notice in just a moment is these items here called foreign blocks. A foreign block is a block that has not yet been replicated from the site of ingest. But even though this job is running, let me go ahead and kill some of these active name nodes. I'm going to do an SSH into let's do the bottom right machine. And I'll just reboot it. So I've just killed an active name node that clients are actively hitting while it's running. But what you'll notice is that there's no interruption on the client side. And similarly, I'll just do one more for completeness. I'll go ahead and reboot a name node over in the Oregon data center. So I've just lost 2 of the name nodes. You can see that they're no longer taking RPC requests, but the job runs unaffected. So what this means is that we have a continuously available HDFS, and that means that from an Hbase perspective, we'll have a continuously available Hbase because we're not going to have the underlying file system go down. So now, we've kind of taken a look at some of these failures, and in the interest of time, I'll just kind of talk through what happens next. When this client comes back up online, or I should say when this name node comes back online, it actually goes through a process of discovery and self-healing. It will learn any transactions that it missed while it was down. It will play those transactions back, and then it will become a fully active participant in the cluster again. So it's self-healing in that respect. So after covering HDFS, let's take a look at Hbase itself. So the application that you see here on screen is a live running application. The difference being is that typically if we think about a given region, that region is hosted at least active by one region server at a time. And if that region server fails, then there's a process that has to go through until we can actually get the region server rehosted somewhere else. The Hbase master has to realize that it's missing. It has to get reallocated to another machine. Once the other machine says, I'm going to host that region, it has to read the write-ahead log. It has to play it into its memcache. It has to read the H files. And then after all that happens, you've got the region hosted again, and then the clients have to be made aware of that change as well. So how long does this take? This typically takes, it could be anywhere from a few seconds, and as Kaz pointed out, it can be anywhere up to, an hour or 2 hours. So it's somewhat indeterministic, if you will. And for, again, a 5.9's reliability application or any mission-critical application that can't withstand any kind of failure at all, then this becomes problematic. So what you're going to see in this demonstration, you can see I have 3 region servers here called Hbase 2, 3, and 4. They are all hosting the same region that these puts are going into. And what is this application doing? It's taking a live Twitter stream. It's taking each one of the Twitter items, it's putting it inside of Hbase, and the application that you see on screen is actually reading it directly out of Hbase and then painting the location on the map where that tweet is actually coming from. So in this demonstration, I'm actually going to shut down the region server hosting this region, and you won't notice any performance impact on the application whatsoever because clients simply keep round-robining their requests to the other active region servers without any interruption. So let's go ahead and do that. I am going to SSH into, let's pick the Hbase 4 machine. I'll get the process ID of the region server here. And I'm just going to do a kill -9 on 9083. And if you take a look here, again, keep watching the application, what you're going to see is that the application is uninterrupted. So I've already killed the process, but if you look at the mapping application, you don't see any interruption to the tweets that are being loaded from it. If you look on the far right on the screen, you see that this region server is now dead. It's no longer taking requests, but the other 2 region servers are picking up that region, or that region was already running on it, and they simply continue operations, both write and read requests to that. And that is effectively the demonstration, a continuously available Hbase, whether it's Hbase master or Hbase region server, so that there are no interruptions of service to your mission-critical applications. Kaz? That's the demo. We are.
Are you not going to show the completion of the HDFS?
We can toggle back very quickly to the HDFS side. One of the things that you'll have seen is that the files have completed over here, and that all of the blocks have also completed. So all blocks have been replicated between all the regions from the HDFS side. And of course, if you look at the 2 machines that I rebooted, they have been completely healed. So they are no longer out of service. They're no longer in safe mode. They have come back into full service, and clients can once again use them. Again, every node, whether it's the name node or if it's the region server, they are all active. The clients are able to hit all of them at the same time. Clients, in fact, round robin their requests to all the active name nodes and all the region servers, and therefore an interruption of any one of them is simply a switch over rather than a failover.
Okay. Thanks a lot, Brett. It's actually always amazes me how people can do the live demos during the presentations and everything works. It's like mind-boggling. Because for me, it always craps out somehow. But anyway, so right, so that's essentially the product. A couple of last words on the Hbase side. Essentially, unlike again HDFS, where the HA has been built since Hadoop 2.0 or HDFS 2.0 rather, Hbase doesn't give us that much luxury. So essentially, all the development that we need to do, we actually do in the open source. So if you want to follow the progress, we have started a set of the JIRAs where we separating Zookeeper implementation out of Hbase. One of the JIRAs is 10866, about to get committed, I guess soon. It's Hbase actually, not HDFS JIRA. And hopefully, we'll keep the stream of the changes coming. And the great part is actually community recognizes the need for it. So there is very warm reception in a sense of this change. Yeah, that's essentially pretty much all. Any questions, guys, at this point? Yeah, please.
I have a question regarding Texas. First of all, I'm interested in what latency introduced by this solution to rules that Hbase, HDFS, and so on. HDFS is not very interesting, but
yeah, Hbase is more challenging. I agree.
it's not so. Okay. Next, what is going on with rule architecture and how?
Okay. I repeat, I think. My question is all about Paxos. First of all, what latency is introduced with this solution first? Second, what is going on with atomic operations? How Hbase logs, interlogs, row logs, how they work with the solution? And third, do you have some optimization for leader election, not Zookeeper leader, Paxos leader election, when client, in case if client would randomly send requests for even the same row for different region server, do they contend for who will propose and which modification should apply it? So it's mostly how your multi-Paxos or maybe ring Paxos, I don't know what you actually do for high throughput, say. Okay. So it's mostly about that.
Right. So just to reiterate, basically you asking about the latencies being introduced by a strong consistency model, right? Yeah. The second question is essentially what we do about the logs on the rows and that kind of stuff, right? And the third one, what about the leader election, essentially, right? So I probably will start from the last one. So essentially, I don't want to go into much of the technical details here. I just leave something to Konstantin to talk tomorrow about, because essentially this is his aim of the presentation. But what we have, we essentially have an ability to configure multiple masters in different ways. So we can have acceptors, in one data centers and proposers actually everywhere else, right? So we can actually cut off the timing of the reaching the agreement, right, significantly. So we have this advantage. But that's essentially the operational issues, pretty much, right? So you can configure it differently. For instance, if you want to have, and it sort of segues to your first questions about the latencies. So if you want to reach if you want to build a system that essentially has the acceptors in 2 or more data centers, right? So which is like totally incredibly robust, right? So you can kill one data center and everything keeps going fine, right? You would pay for it because you would have to do round trip and round event, right? And it is costly, apparently.
How much round trips cost?
That's where I'm coming to. So essentially, optimally, I guess, the best case scenario, right, once the leader has been elected and quorum is built, right, so you run in one round trip per agreement, right? Worst case scenario, I think, or on average, I guess, you can get up to 2.5, right? So which means that if your typical latency on WAN is, say, 80 milliseconds, right, so you can actually go up to 200 milliseconds per request. Right, which is sort of bad, but if you think about like what you get in exchange, right, it's quite interesting. So, or quite beneficial anyway. So now about the lock-in mechanism and stuff like this, because we guarantee strong consistency, right? So we essentially guarantee that each operation, right, would be atomic, essentially, right? So the operation could happen or could not happen, and will it be successful or not is actually determined before the operation taking place.
So here some sort of serialization on top of case, say.
Sorry, what again?
Some sort of linearization. It's more.
Some sort of linearization. Yeah, I guess you can say so. Right? No.
Thank you.
Yeah, sure. Anyone else? No? Okay. Thank you, guys. Appreciate it. Great crowd. Thank you.